welcome to the first half of our show. This is Metaphysics, and I'm Jesse. So this will be the new way I'm going to try to number these episodes so I can keep track of what I'm doing, and so that I'll get more out per year, hopefully. So this is not the 13th season, but it is in fact the year 2013, and this is the second episode I've done this year. So today I'm going to talk about cognitive dissonance. So cognitive dissonance is something that can happen while you're doing a physics problem, and it's something that you kind of need to be thinking about while you're doing physics, so it's a metacognitive process. And cognitive dissonance is when you can get two ideas in your head, or you can come to two conclusions in a problem that are kind of mutually exclusive or that contradict each other. And so what we're going to go over this problem is how to kind of work through that and come to a conclusion that is kind of self-consistent. And the problem we're going to do today is the standpipe problem. So these two things are standpipes. The idea is we have this big reservoir, and there's some ideal fluid in it, and it's going to flow through this big pipe into the smaller pipe, and there are two standpipes, which are basically just vertical thin pipes that are attached, and the water level will rise in these pipes to some height h1 and h2, and these are not meant to be exactly equal. They could be, h2 could be bigger or smaller than 1. And we want to know two things. We want to kind of figure out what does h1 and h2 measure, and then also how are h1 and h2 related if we're given like this pipe is bigger than this pipe, given that the water is flowing out here at the other end. So we want to do two things. So what does h measure, and how does h1 compare to h2? So let's go through this problem and just kind of write down things that we know. So let's call the height of the reservoir water h. This is the frog. The reservoir, and the two standpipes are all exposed to air. So the pressure up here will be PATM, the pressure up here will be PATM, and the pressure up here will be PATM. So that's 1 atmosphere. I've labeled these locations. So the water at the top of the reservoir is at point A. The water at the top of the standpipe 1 or standpipe 2 is points B or point C, and the water coming out of down here is at point D. I've labeled the height of the standpipes h1 and h2, little h1 and h2, and the fluid or the water inside of these two pipes, I'm going to say is going to have P1 and V1, so the pressure down here and the velocity, and the same thing in this pipe is going to be P2 and V2. So let's go through and analyze this problem. So here's a small schematic so we can remember what we're doing. So to figure out what B and C are measuring and maybe try to relate h1 and h2 to each other, we'll use Bernoulli's equation, which is an equation that we can use for ideal fluids. And we'll try to use point A to make this comparison. So let's write down Bernoulli's equation first at point A. In black. So Bernoulli's equation has three terms. There's the pressure. So the pressure at A is 1 atmosphere, or PATM, because it's exposed to the air. The next term in Bernoulli's equation is the velocity term. But since if we're going to make the large reservoir approximation, which we can in this problem, we assume that the velocity at the water at the top of the reservoir is 0. And so all we have left over is the potential energy term, which is 1/2 G, or 1/2 rho G H. So that's like the mgh term, and the height there is capital H. So now we want to relate that at point A to Bernoulli's equation at points B and points C. So at B, again, it's exposed to the air. So I have 1 atmosphere. A standpipe, so the assumption we make about our standpipes is that the water is not flowing. So they kind of measure some steady state thing. So if h1 is changing, that would mean like hopefully big H would be changing, or V1 or P1 would be changing. But we want to understand this as kind of like a steady state problem. So we're going to say that h1 and h2 are fixed. If that's true, then there's no velocity at the top. But we do have a potential energy term for the top of the standpipes, which is h1. And so now at point C, which is the second standpipe. Again, it's exposed. And the only difference is it is at H2. And so the way we're going to use Bernoulli's equation is Bernoulli's equation in an ideal fluid has to be constant throughout the fluid. So we are going to set these two things equal to each other and also these two things equal to each other. And so by extension, A and C would also be equal. So if we examine these three equations, they all have this PATM. So we could cancel it from all of them. And we're just left with this 1/2 rho G times H, H1, or H2. So that tells us that if these equations are equal, H, H1, and H2 have to be equal. So this tells us two things. One, to answer our question, H1 and H2 are just measuring the reservoir height H, and we've also learned that H1 will always be equal to H2. Okay, so this is one way of solving the problem. We can maybe think about this problem in a different way and see if we arrive at any cognitive dissonance. So I haven't yet used this point D, or the fact that there's some water flowing out of the end of this pipe. So now, rather than using point A to get some information about B and C, I'm going to use point D. So it won't be important exactly what the value is, but if this is open, water will be flowing out at some velocity v2. Based on this picture, I know that A1 is greater than A2, where A1 is the circumference of this, or sorry, not the circumference, the area of that pipe, and A2 is the area of this small pipe. So if continuity, so if these pipes are, or if the water flowing through point 1 is also going through point 2, we can use the continuity equation to relate V2 to V1. And since the area of 1 is greater than the area of 2, I know that the water at V2 will be flowing faster than at point 1. So I know V2 has to be bigger than V1. I also know I can use Bernoulli's equation to relate the point down here. We could call it point 1 to the point in the smaller pipe, point 2. So I know P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. So I've neglected the potential energy term because I'm calling the bottom of the pipe here, or kind of this point, where y equals 0. So there's no potential energy at this bottom surface. So if this relationship is true by Bernoulli's equation, and if V2 is greater than V1, so if this term is greater than this term, this implies that P2 has to be smaller than P1. So if V2 is greater than V1, V2 squared, and velocities are both positive in this case, V2 squared will also be greater than V1. So that means P1 has to make up for V1 being smaller. And so P1 will be greater than P2. So now if I think about having some amount of pressure down here at 1, and this pressure is pushing this water up the tube H1, and the pressure down here at P2 is also pushing this water up to H2, well, it makes sense that if P1 is bigger than P2, it should be able to hold more water. And we can assume that these standpipes have the same area. So we can kind of think about it in forces or pressures. So if this is the case, then we know that H1 is going to be greater than H2. So this way of thinking about things tells us that really if H1 is greater than H2, the way we got to that was by thinking about the relationship between the velocities. So now H1 and H2 seem to measure V1 and V2 in their respective parts of the pipe. And if the way I've drawn this picture is correct, H1 is greater than H2, and really it just will go back to depending on the area of this pipe and the velocity by the continuity equation. So this is where we hit cognitive dissonance. So we've come at this problem from two different ways. We are getting different answers that contradict each other. So now what we realize is that we should be saying what. So now the question is, how do we move forward from here? How do we resolve this cognitive dissonance and figure out the answer to the problem? So the method I'm going to use, so I mean, depending on the problem you run into, there might be more than one way to think about kind of resolving this dissonance, but the thing that we're going to do today is examine the assumptions that we might have made, or like the assumptions we might not have thought carefully enough about when we were doing this problem. So I said Bernoulli's equation works. So what are the assumptions? Bernoulli's equation needs to be an ideal fluid. Well, I mean, we basically used that in the problem. We say this is like some ideal water, so that's okay. I think we can say that assumption is not going to cause us problems. One thing that we might not have thought about is that Bernoulli's equation doesn't. So I think I said that Bernoulli's equation can be used to like connect any 2 points in a fluid. So actually, the real assumption, or the real statement of that, is Bernoulli equation only will work along a streamline. What does that mean? So a streamline is kind of like water could potentially flow from one point to another point. And if that's the case, then I can connect those 2 points using Bernoulli's equation. So let's kind of zoom in on a standpipe. So this thing up here is our standpipe. Here is either the pipe at 1 or the pipe at 2. It doesn't really matter. So if I think about the water over here at some time later, where does this water go? And the question is, does it go up into the standpipe? And so could I use it? Could I use Bernoulli's equation to call this kind of like a stream and relate these 2 points by a streamline? Well, all of this water here, since the standpipe is not changing in height, the water in the standpipe must be standing still. So all of this water here will actually flow all the way by the standpipe, and none of it will go up, and none of the standpipe water will come out. So there are no streamlines that would kind of go either in or out of the standpipe. So those don't exist. So what is happening at this boundary? So you could actually imagine kind of like an imaginary membrane here. So water will flow past this membrane, and water above it will just sit here, but there is no way for water to go either up or down, or water won't go down or up. So this is actually not going to work. It can't connect any 2 points in a fluid, but it will connect any 2 points along the streamline. But we can't relate the points up here to the points down here. There's no streamline connecting those two. So the question is, how do we proceed? Well, we proceed by using kind of the trick we did in the second example, actually. So we know even if Bernoulli's equation doesn't work, we can still rely on Newton's laws. So if I have the pressure above this kind of imaginary boundary, and I have the pressure below, because this water here is not moving, these pressures must be equal. So they must not be, if they weren't equal, then the water would be flowing up or flowing down. But since this thin slice of water is in equilibrium, the pressures above and below it must be equal. So that if that's the case, then we can kind of go back to thinking about this problem using D to compare, because how we did D was we said, oh, well, P1 and P2 must be different, and so the pressure pushing up in 1 will give H1 a different height than H2. So the resolution to this dissonance is that we need to really not use Bernoulli's equation to connect to these things, but Newton's laws. And we actually do find out that H1 does not have to be equal to H2, depending on whether the pipe at 1 or the pipe at 2 is thicker or thinner. That will tell us whether H1 should be greater or less than H2. And we also know that H is really measures the pressure down here at the bottom, kind of most directly, and that pressure then will in turn depend on the velocity of this pipe, and that depends on the area of this pipe. But standpipes, their function is to really measure the pressure down here, or if you know it's at a set pressure, then it could also measure velocity. So that is kind of the function of a standpipe, and examining our assumptions was the way we kind of got past this cognitive dissonance. And rejected the idea. So we rejected this idea that Bernoulli's equation can be used to relate this. So we know, in fact, that this is not true, and H1 does not have to be equal to H2. So thanks for watching, and please leave me any comments if you have them.